time to begin looking at the general equations of motion that we'll be using for objects that are translating, rotating, or combinations of the two. Newton's third law is going to then be utilized yet again. We already know this as the sum of the forces equaling mass times acceleration. Let me just reiterate that in its purest forms, the sum of the forces equals the derivative of momentum with respect to time. You could have momentum in either of those scenarios. But we're not going to be working with changing mass, so that's not going to be an issue. We'll just stick with the sum of the forces equals mass times acceleration. But keep in mind, everything that occurs in a translational environment will also occur in a rotational environment. And so as I have forces in a translation or linear environment, I'm going to have moments in a rotational environment. So a moment is nothing but a rotational force. The units are different, and the way we derive it is different, but in concept it's exactly the same thing. And then we've talked about moment of inertia, and a moment of inertia is really just a rotating mass. Keep in mind, the whole concept of inertia is the tendency for an object to continue moving. So when Galileo discussed inertia for translation, a large mass would continue moving unless a force acted on it. If the mass was large, then you needed a large force in order to change that motion. Well, the same thing holds true in rotations. In rotations, a large rotational inertia is more difficult to change its motion. That is to say, if I want to take a merry-go-round or a flywheel and get it moving, if it has a large rotational inertia, it takes a lot of moment, not force, but moment, to change that angular motion, to get it started or to stop it. And then the right side of the equation for Newton's second law in linear motion or translation is acceleration. So under rotation, it's going to be angular acceleration. So let's take a look at an example. And one of the things we're going to look at in this example is this last statement right here. For bodies undergoing an acceleration, the sum of the moments must have its origin chosen carefully. And I'm going to actually do this same problem choosing origins in two different locations. Okay, so the first thing we're going to do with this problem is, of course, read through it. You guys can do that just as easily as I can. Let's take a listing of what we're given. So we know that the weight of the airplane is 2,800 pounds. Begins its takeoff at t is equal to 0, so if it's beginning its takeoff, that would imply then the initial velocity is equal to 0, and that's at time t equals 0. The horizontal force T, this is the thrust of the engine, is equal to 1,000 pounds. And we're going to neglect other horizontal forces, for example, on the wheels by the runway or air resistance on the rest of the craft. And then what we're looking for is the distance the airplane has moved in 2 seconds, and the normal forces exerted on the tires at points A and B. So the first part of this problem we've done 1,000,000 times, and that's all right. We'll do it 1,000,001, and we're going to look at it here. But the second part's a little bit different because we've always considered a normal force when we talk about a point object. But we're going to have two different normal forces at A and B here, and that's one of the things that we're going to want to look at as we work this problem. The fact that there's a different normal force at A and B will become one of the characteristics of this kind of a problem. So let's start with our force diagram. We already have the thrust defined, and we're going to call that T. And that thrust is actually a normal force, and the normal force is caused by the air, so that's due to the air. That's a thing, and it's acting on the plane. And of course the weight is given here, so that's a gravitational force, and that's due to the Earth acting on the plane. And then we're going to have a normal force here, and I'm going to call that F and A, and another normal force here, and I'm going to call that F and B. And even though the two forces are different, I can define them the same way. They're both normal forces due to the runway, or the ground, acting on the plane. Now they are not equal. I define them the same way, but their characteristic lettering here, FNA and FNB, is an indicator that they are not of the same value. And they also do not act at the same place. Alright, and that's all of my forces. Those are all the forces acting on the airplane. Now, a couple of things become critical here. As before, I need to define an axis. So we'll make the x-axis to the right, and the y-axis is straight up. But something that I haven't worried about too much in past force diagrams, I really need to consider here, and that's the mass times the acceleration. Now remember, we've always talked about mass times acceleration, and I generally try to draw that in red. But one of the things that we're going to do here is I'm going to draw the MA here in red, and I always have it emanating from the object's center of gravity. And so the center of gravity is this location right here. This symbol of a circle with two shaded quarters, that's kind of a universal symbol for the center of gravity. And oftentimes your book will label that G. So capital G for the center of gravity. Now that location really is going to become important here in a minute. Let's take a look at the force equation then. That will go along with this diagram. So the sum of the forces in the x, I'm going to have negative t because it's acting to the left, and that's really it. And that's going to equal mass times acceleration down. Remember, my mass and acceleration were to the left. So ma was in this direction, and let's put in my two forces that I labeled before. And so the sum of the forces in the y direction, notice the acceleration is strictly in the x direction, so I'm not going to have any y component to my acceleration. So the sum of the forces in the y, I have Fna plus Fnb minus w, and that's going to equal 0. So the first part of this problem really isn't too bad. I know my thrust is 1,000 pounds, and the weight of my aircraft is 2,800 pounds. Of course, it's mass times acceleration, so I divide that by the acceleration due to gravity. And from there, I should be able to find my acceleration. So the acceleration should equal 1,000 pounds over 2,800 pounds times the acceleration due to gravity. And that'll be 11.5 feet per second squared. So from that, I can answer the first question. First question, remember, was what is the distance moved in the first 2 seconds? So x equals x naught, we'll assume that that's at 0, plus v naught t, that's also 0, plus 1/2 a t squared. So I'm talking about the first 2 seconds. So x is equal to 1/2 a, which is to the left, so I'm going to put minus 11.5 feet per second squared times 2 seconds, and I square that. And so I'm going to get minus 23 feet. I have seconds here, and that's squared. I have seconds here, but that's also squared. So the second squareds will cancel, and I'll just be left with feet. A minus sign indicating that it's to the left. But the distance traveled was what I was looking for, and that's 23 feet. Now the sum of the forces in the y, I know that Fna plus Fnb is going to be equal to 2,800 pounds. But the question is, what are the individual normal forces? I only know that their sum is 2,800 pounds. How do I find the individual forces? And this is where the sum of the moments will become important. Now in the first part of this, I'm going to sum my moments around G. So the sum of the moments about the point G. And when I do that, clearly the gravitational force here is going to apply no moment, because remember, moment is R cross F, so lever arm times the force. And since W is acting at point G, the distance between G and W is 0, because it's right there. I can see that there's 2 feet between the force at B and the G. Okay, so now Fnb acts in this direction. You might recall that this is referred to as the line of action of that normal force. So the line of action of Fnb. And all of these forces have a line of action. So here's the line of action of Fnb. Here's the line of action of Fna. Here's the line of action of the thrust T. So we'll tackle each of these one at a time. So the line of action of Fnb is along here. It's 2 feet between G and that line of action. So the lever arm for Fnb is 2 feet. And so I get 2 feet times Fnb, which I do not yet know. And Fnb, since the line of action is up like this, and the center of this rotation is here, Fnb wants to act in the counterclockwise direction, and so that's a positive moment. Fna now has a line of action over here, and it wants to rotate in the clockwise direction. So what's going to be minus sign, because it's going to be a clockwise moment. And the distance between G and FNA is 5 feet. So there's the moment equation for FNA. And finally, here's T, line of action for T, and T is 3 feet, 4 feet. So T is 4 feet above the ground, G is 3 feet above the ground, so the line of action must be 1 foot. T wants to rotate it in a counterclockwise direction, so it's a positive moment, 1 foot, and that's 1,000 pounds. Okay, and all of this is going to equal I times alpha, the moment of inertia times alpha. But the plane is not rotating, so I really don't need to worry about that. So I alpha is going to be equal to 0. And so what I'm going to end up with is FNA plus FNB equals 2,800 pounds. That's coming from this equation. And then this equation will yield 5 feet times FNA minus 2 feet times FNB, 1,000 foot-pounds. Now be careful of the units. 1,000 foot-pounds is a moment unit, and pound-feet we used earlier for energy. But if I divide both sides of this equation by 2 feet, then I'm going to get 2.5 FNA minus FNB, and that's going to equal 500 pounds, because the feet units will cancel out on both sides. And so what you'll see here is that I have 2 equations and 2 unknowns. If I add equation 1 and equation 2 together, I'm going to get 3.5 FNA. See, I have a positive FNB and a negative FNB, so those will cancel. And then 2,800 pounds plus 500 pounds, so that equals 2,300. So that equals 3,300 pounds. And so FNA equals 3,300 over 3.5. And that's about 943 pounds. And then, of course, FNB is that taken from 2,800 pounds. Okay, but let's do the problem again. So I draw in my forces. Here's FNA, and here's FNB. I've got W and T in there. But this time, let's put the moment at A. So I want to do sum of the moments about point A. So the sum of the moments about point A. Now when I do that, so here's point A. Notice the only thing I don't know, because I know T, I know W, I don't know FNB. The only unknown here is FNB. So FNB is wanting to rotate in the counterclockwise direction about A. So the sum of the moments about A, I've got 7 feet times FNB, and then W wants to rotate in the clockwise direction, so minus 5 feet times W, which is 2,800 pounds. T wants to rotate counterclockwise, and that's 4 feet above point A, so plus 4 feet times 1,000 pounds. And that's it. So that should equal I alpha, but there is no alpha. The plane is not rotating. It's not going to rotate. But this is a different equation than the previous equation, so I'm not going to get the same answers. But one of the things we're not taking into account here is the MA. The right-hand side of the equation also has to include R cross MA. So I should be adding into here plus R cross MA. And when I do that, I'm going to get 3 feet, and it's in the counterclockwise sense, so equal to 3 feet, of course this is 0, times MA, but remember from previous calculations, A is 10 over 28 times G, so this will be M, which is 2,800 pounds, over G times A, which is 10 over 28 G. And so as I simplify this equation, I get 7 feet times FNB minus 14,000 foot-pounds plus 4,000 foot-pounds equals, here the G's will cancel out, the 28 cancels there, that leaves me with 100. So that's 1,000 pounds, so that's 3,000 foot-pounds. And so if I solve this for FNB, I get 1,857 pounds. And if I add this to the FNA I saw earlier, I add up, that gives me 2,800 pounds. So I get the same answer no matter how I slice it. So you can choose any point you want as your axis of rotation, or where do you want to sum your moments, about what point. But you cannot forget about the MA if you do it any place but at the center of gravity. Choose where you want. Some places are easier than others. In this case, choosing point A as my moment origin gave me my FNB immediately, whereas choosing it around the center of gravity, I had to solve a system of two equations and two unknowns. So it might be easier in one place than in another place. But if you don't revolve around or find your moments around your center of gravity, then you've got to keep in mind that R cross MA comes into play on the right-hand side of the equation. This was discussed a little bit back in statics, but back in statics, the right-hand side of the equation was always 0, so it never mattered about where you chose to sum your moments. So here it does make a difference. You'll get the same answers no matter where you do it, but it does make a difference as far as the mathematics. I could also have done it around B and gotten the same answer. I could choose any arbitrary point I want, and I'll still get the same answer. But choosing a point like this one out here doesn't help me at all. There's no simplification in my process. Choosing either A or B does simplify things because it eliminates one of the forces, one of the unknown forces, from my moment equation. And that's kind of nice. Okay, so let's take a look at another example. Let's start off with a force diagram. So I have an arm ABC, and it's got a mass of 320 kilograms. So there's going to be a weight, and I always put my weight at the center of gravity. So mg would be coming there as 320 kilograms times g. The moment of inertia about the center of mass is given, 360 kilogram meters squared. That would be a squared there. Point A is stationary, so that's my pivot point. And the hydraulic piston exerts a 14 kilonewton force on the arm, and that's going to be in the direction of the piston. So that's a tension. It's actually a compression, but I'll write it in as T. And of course there's going to be a force here at A. There's going to have an x and a y component, so I'll label it A sub x and A sub y. So A sub x and A sub y are the components of a normal force, and that's due to the pin at A acting on the arm. And then mg, of course, is a gravitational force. That's due to the earth acting on the arm. And then T is going to be a compression. Still a tension, it's just in the negative direction, or in this case pushing. And that's due to the piston acting on the arm. And what we're interested in is the angular acceleration. We could do the sum of the forces. Of course, if I'm going to do forces, I need an axis. So x in this direction, y in that direction. So the sum of the forces in the x, I have A sub x plus a component of the tension in that direction. I'll call this the angle theta. So T cosine theta, and that'll equal the mass times the acceleration in the x direction. So A is moving, and so there is an acceleration, and I don't know what that direction of that acceleration is. So I'm going to go m a sub x that way, and m a sub y like that. So the sum of the forces in the y direction, I'm going to have a sub y plus t sine theta minus mg, and that'll equal m a sub y. And then finally the sum of the moments, and I'm going to sum my moments. I'm going to sum them about g, that way I don't have to worry about the MAs. Now if I do that, a sub y wants to rotate it in the clockwise direction, so minus a sub y, and the line of action for a sub y is here, and here's my axis of rotation, if you will, so that's 1.8 meters away. And then a sub x wants to go around counterclockwise, so plus a sub x, and the line of action for a sub x is here, and below the center of gravity, that's 1.1 meters. And then there's the piston force, and there's an x component, which is in this direction, and a y component, which is in that direction, for the piston force. And the x component was t cosine theta, and the x component wants to go around counterclockwise, so plus t cosine theta, and the line of action for the x component is 0.3 meters underneath the center of gravity. And then t cosine theta, or t sine theta, excuse me, t sub y is going to want to go clockwise, so minus t sine theta, and here there's a distance of 0.4 meters. And that's it. mg is the only other force, and that's acting at the center of gravity. And so all of this is equal to I alpha. Okay, so as I examine this system of equations, I can list my unknowns as a sub x, a sub y. Those are the pin forces at point A. I also don't know little a sub x and little a sub y. Those are the accelerations at the center of gravity, and I don't know alpha. So I've got 5 unknowns and only 3 equations. But keep in mind what we learned last chapter. As I examine this system, if I want to know the acceleration of g with respect to a, that's going to equal, this is a vector quantity, that's going to equal alpha, which is what I'm looking for, crossed with the position of g with respect to a, vector, vector, minus omega squared times the position of g with respect to a. Now in this particular problem, we're not given an angular velocity, and so we're going to assume that it starts from rest. So that term is going to be 0, and so the acceleration of g with respect to a is equal to I, j, k, 0, 0, alpha, and then in the x direction it's 1.8 meters, in the y direction it's 1.1 meters, and then 0 in the k, and so this equals 0 minus, so minus 1.1 meters alpha in the I hat direction, but that's a sub x, and then plus 1.8 meters alpha in the j hat direction, and that's a sub y. And so now I've got a sub x and a sub y as 2 equations. So a sub x equals minus 1.1 meters alpha, and a sub y equals 1.8 meters alpha. So there's 2 more equations to add to my list of equations. So now I have 5 equations and 5 unknowns. Okay, what if I have an object rotating about a fixed axis? What can I do? Well, first thing I want to do is find out what relationships might exist between the acceleration and the angular acceleration and the angular velocities. So these relationships are very important. We'll see those in the examples. And then, like I've just finished doing, I'm going to do the sums of the forces and the sum of the moments. And when we sum the moments, we have to choose a point about which to sum them. It generally will be either the axis of rotation, because this is in fact rotation about a fixed axis. So we'll either sum the moments about the axis of rotation, and if we do that, we have to be very careful because we cannot forget r cross ma. Or we'll sum the moments about the center of mass. And then we're going to use Newton's laws. Okay, now one thing to keep in mind here, the normal tangential coordinate system will be the preferred coordinate system in most of these kinds of problems. And you'll see that here in the example. Here are Newton's laws. Newton's second law here, F equals ma. That's a vector quantity. And we'll break it down into its normal component, which is mr omega squared, or m omega squared times the position of the center of gravity, or the tangential. So those will be what we'll use instead of x and y for the most part. And then we'll have the sum of the moments. And again, we can either choose summing the moments around the center of gravity or summing the moments around the axis of rotation. Be very careful. If I sum the moments about the axis of rotation, then I need the moment of inertia about the axis of rotation. And for that, we'll need to use the parallel axis theorem. When I do that, when I count the parallel axis theorem into this I0, r cross ma will be included in there. Because as it rotates around, so here's the center of gravity, but here's the axis of rotation. So there's r. As it goes around, there's going to be some sort of a tangential acceleration. The normal acceleration doesn't apply a moment. R cross ma is 0 because a is in the same direction as r. It's actually at 180 degrees, but the cross product goes away. So only the tangential will actually apply a moment, and so r cross ma will have a magnitude of r sub g times m times a, which is r times alpha, because this is going to be this a here. All that counts will be a tangential. And so that's the same as r times alpha. Well, what do we get? We get m times r sub g squared, because this is also r sub g. But the moment of inertia about O is equal to moment of inertia about g plus mr squared. So there's the mr squared times the alpha, so times alpha, and that's just equal to I sub O. times alpha. So the beauty of I sub O and the parallel axis theorem is that R cross MA term is built in, and that's going to make life nice. So here's a nice example. I have a 25-pound double pulley, and it starts at rest, so my initial velocity, in this case it's angular velocity, will be 0. It starts at rest and it's in equilibrium, and then what we do is we apply a couple, a constant couple. So we're going to neglect any friction, and we know the radius of gyration of the double pulley is 6 inches. So what that tells me, the moment of inertia about the center of gravity is equal to the mass times the radius of gyration. We'll use the letter K for the radius of gyration. So that's mass times K squared. So this would be 25 pounds divided by the acceleration due to gravity times a half a foot, because it's 6 inches squared. So what's the angular acceleration of the double pulley system and the tension in the rope? Now when we initially started this problem, we said it was in equilibrium. And so in that case, the tension of the ropes would be equal to the weight. So if I have a 10-pound weight here, the tension up is 10 pounds. Here it's 5 pounds. But we're no longer in equilibrium. The tensions are no longer equal to those weights. So as I look at the forces, there's going to be a T sub A over here and a T sub B over here. And then there's a moment that's being applied around here. And as I look at A, there's going to be a T sub A up and a W sub A down. And as I look at B, there's going to be a T sub B up and a W sub B down. And if I define those forces, T sub A is the tension due to the rope acting on the pulley or acting on WA, weight A. T sub B is a tension due to the rope acting on the pulley or acting on weight B. And of course, WA and WB are gravitational forces due to the Earth acting on weight A or weight B. We don't really know where M is coming from, but we would be able to define M as well if we knew what its origin was. But any applied couple also has to follow those same definition rules. So now what we have to look at are the equations. Well, as far as the pulley is concerned, there is in fact the weight of the pulley here, which I'll call WP, and there's also going to be a normal force here that's due to the axle or the pin at the axle acting on the double pulley. But I'm really not too concerned about those. I mean, I might want to know what the normal force is, but this problem doesn't ask. And the beauty of that is that means that I don't really need to look at the sum of the forces in the y direction. Of course, there are no x forces when it comes to the pulley. So all I really care about is the sum of the moments. So the sum of the moments, and I'm going to choose the center of gravity of the pulley, which is also the axis of rotation. So the sum of the moments become, well, WP and FN are right at the center of gravity, so they apply no moment. There is, of course, this moment here, so we'll call that M. And then tension A is acting down, and that is going to supply a moment. And it's a counterclockwise moment. And so that's going to be T sub A times 4 inches, which is 1/3 of a foot. And that's positive because it is counterclockwise. And then T sub B is also acting down, but around this direction, that's clockwise. So minus T sub B, and that is at a distance of 8 inches, so 2/3 of a foot. And all of this is going to equal I sub G times alpha, which of course I know what I sub G is. So I don't know tension A, I don't know tension B, so there's 4 unknowns here. M, T sub A, T sub B, and alpha. So I'm going to need 4 equations. So what I have to do now is I have to look at the masses themselves. So if I look at A, I can see that T sub A is up, W sub A is down, and that's going to equal M sub A times the acceleration of A. I do know what WA is and M sub A, but I don't know the acceleration at A, so I seem to have added another unknown. Similarly over here, I have T sub B minus W sub B, and that's equal to M sub B, A sub B. Now keep in mind the direction of the moment is counterclockwise, and since it's counterclockwise, the acceleration of A is down, the acceleration of B is up. And so I really want a minus sign out in front of that. But the other thing I know is the relationship between the angular acceleration and the linear accelerations of A and B. If this is moving around at some angular acceleration, there's some angular acceleration alpha, then I can see that A sub A is equal to R times alpha. And I'll just work with magnitudes there. Similarly, let me step back. R here is equal to 4 inches. Over here on the right-hand side, A sub B magnitude is equal to 8 inches times alpha. So I now have 5 equations. 1, 2, 3, 4, 5. And how many unknowns do I have? 1, 2, 3, 4, 5, 6. So I have 5 equations but 6 unknowns, and so the angular acceleration here, or the tension in the pulleys, all of these will be in terms of this couple. Because I don't know the value of that couple. Keep in mind, if I double the value of the couple, all of those equations will change. So I'm going to get all of my answers in terms of the value of that couple that I've applied. If I know the value of the couple, then I eliminate this unknown, and I end up with 5 equations and 5 unknowns. So as it stands, I'm going to solve for these unknowns all in terms of big M, the couple that is applied to this pulley system.